Now we discuss the boundary term of the gravitational action. Why is that necessary? Well, the problem is that, strictly speaking, the variational calculus for the gravitational action is not well defined because the Lagrangian depends on the metric, on its first derivatives, but also on its second derivatives. It wouldn't be a problem if they were only space derivatives, but by Lorentz invariance you also have time derivatives. So it's like having, in one dimension, a Lagrangian that depends on Q, Q dot, and Q double dot. Why is that a problem? So let's consider, for example, the simplest non-relativistic Lagrange. And of course, the action will be the integral from t0 to t1 dt L, which is an L of Q of t and Q dot of t. Then you make a variation of the action, and what do you obtain? The integral from t0 to t1 of what? So you have partial L, partial Q, delta Q, partial L, partial Q dot, delta Q dot. And what do? You integrate by parts, because you know that this is equal to the time derivative of delta Q. But let's keep track of the boundary term when we integrate by part. So the first contribution gives the Lagrange equations. But you have an extra contribution, which is the integral from t0 to t1 dt. That is the integral of a total derivative, which is equal to the total derivative of this thing, partial L, partial Q dot, delta Q. Okay, that's not the end. So with that we can compute, because it is a boundary term, integral from t1 to t2 dt delta Q, the usual Euler-Lagrange equations, plus. So you have this delta partial L partial Q dot delta Q evaluated at T2 and T1. Did I call it T2, T0, T1, T0, T1? T0, T1, t0, t1. And that should be 0 for every variation. So what do you do to ensure that that is indeed 0? You have to demand that delta Q is 0 at both extrema. Which means that your boundary values are fixed. And you have to require that your Lagrange equations be satisfied. That's a well-defined variational problem. Why? Because it has solutions, and it's not a Cauchy problem. You will have the field equations with the Dirichlet conditions, yes. Instead of having a Cauchy problem, which means you know the position and the velocity, the initial position and the initial velocity, you know the initial position and the final position. Still, it's a well-defined problem. Now, let's take the same theory and add a boundary term. And apparently, we don't do anything wrong because we just add a total derivative, and instead of writing q dot squared divided by 2, we write this. It's the same thing up to a total derivative, because if you partially integrate, q dot squared becomes minus q dot squared. Q dot dot becomes minus q dot squared. But now, so now you have, let's say, L prime. S prime is equal to the int t0, t1, L prime. Which is an L prime of q of t, q dot dot of t. And let us see what happens of the variation. So, what do you get? You get the partial L prime, partial q, delta q, fine, plus partial L prime, partial q dot dot, delta q dot dot. So now you integrate once by parts. dt partial L prime partial q delta q minus d over dt partial L prime partial q dot dot delta q dot. And then there is the integral from t0 to t1 of dt and the total derivative of partial L prime partial q dot dot delta q dot. Yes. That's not enough. You have to integrate by parts once again. And let's see what we get. The integral from t0 to t1 dt of what? If we integrate by part once more, you have plus 2 derivatives with respect to time of that. And we will factorize finally a delta q. So we have delta q partial L prime partial q plus second time derivative of partial L prime partial q dot dot. That is the first contribution. Then you have a boundary term and you have the second boundary term. So let's write the second boundary term first, which is partial L prime partial q dot dot delta q dot t0 t1 and then you have another boundary term from here. You will have the total derivative of this without the dot here. Let's say the total derivative of this without the dot, with a minus. So that will be equal, so minus partial L prime partial q dot dot, no, that's the total derivative. Since this is a partial integration, we lose. That's the total derivative of this with d over dt. T1, T0. Check. Yes. And that should be identically 0. But if that should be identically 0, that means that delta Q at T1 should be equal to delta Q at T0 equals 0, but also delta Q dot at T1 to have this boundary term disappear. Delta Q dot at T1 delta Q dot T0 equals 0. And the version of the Euler-Lagrange equations, which will be totally equivalent to the other one, the one we had before, because L prime now is this one. So in the end, you will have the Q of T1 is identically something like Q1. Q of T0 is identically some fixed number. Q dot of T1 is something like this, something fixed. Q dot of T0 is that. And the equation d partial L prime partial Q is equal to minus d squared d dot squared partial L prime partial Q dot dot. And we can check what this gives. dl prime divided by partial L prime divided by partial Q is equal to minus the gradient of the potential, because this is the Lagrangian, and the derivative with respect to Q dot dot is minus q over 2 minus q dot dot over 2 but there is something here that is missing, because there is a factor 2. Oh yes, because I forgot the extra term in the Euler-Lagrange equations. Okay. There is an extra term or not. So yes, no, there is no extra term. It's only that there is an extra term in the derivative with respect to q, because you have to take the derivative also there. So the extra term is dl prime divided, partial L prime divided by partial q is minus q over 2 minus q dot dot over 2 minus the gradient. Okay. That is equal to minus the second derivative of minus q over 2 again, and that is equal to q dot dot over 2. So in the end, you get q dot dot is equal to minus the gradient of of the potential. So the equations are the same, but you have boundary conditions that make it impossible to solve them, because you are fixing the position and the velocity both at the initial and final times. And unless somebody gives you those implied by the very same equations you would like to solve, you will never be able to solve them. So that's redundant or impossible to solve. But this is the case of gravity. So gravity has this kind of problem, strictly speaking, when you have a Lagrangian like that, which we have neglected, or we could use an action that we call the gamma-gamma action, where we threw away the boundary term, and we could work with a Lagrangian that depended only on q and q dot, basically. So we had this kind of action. Minus 1 divided by 2 kappa squared, integral on your manifold of what? First, there is a total derivative, and then the gamma-gamma terms. Let us recall what this W lambda is, because it will be used. W lambda is the square root of minus g mu nu gamma mu nu lambda minus g mu lambda gamma mu nu. So this part is okay, but it is not manifestly covariant. And this part is the boundary term. And the total is manifestly covariant, but it has a non-well-defined variational problem. So what can we do? The integral of that is equal to the integral on the boundary. So that's a total derivative, so it can be written as an integral on the boundary of what? How to write that in a completely covariant form? The surface element, integration element, is equal, now we check it, but first I write it, is equal to this. Partial x alpha. There is a wedge understood, but you know that it is understood. So that is indeed that thing. That is the correct surface element, but first, this is not a vector. This is not a vector. But if that to check that this is the correct surface element, if v lambda is a vector, then the integral on the boundary of v lambda sigma lambda is invariant under diffeomorphisms. Why? Because that is equal to the integral on the boundary of square root of minus g, 3 factorial, whatever, epsilon mu nu rho sigma v mu d x mu nu dx rho dx sigma. And what happens when you make a change of variables? Generic diffeomorphism, what happens is that these four objects behave like vectors. One because it's a vector, the other is a dx mu, and that transforms, well, as a differential actually, so that's not strictly a vector from the mathematical point of view, it's like a form. And so you get a Jacobian so a matrix, the Jacobian matrix, let's say J for everyone. And then you use this identity that we have met already. So let's say J alpha beta is the Jacobian, mu alpha J nu beta J rho gamma J sigma delta, that is equal to alpha epsilon alpha beta gamma delta times the determinant of J. So you go back to the same expression because square root of g will provide the determinant of j also, j to the minus 1, because again these are not vectors but these are forms, so they have upper indices. So that is okay, but that is not okay here again because sigma lambda is written in the proper way. W lambda is not a vector, so how to improve the action? The action will finally not be this one. So what we do is the following thing: we will look for a different boundary term. One that transforms correctly. So with a vector. Such that the variation of the wrong boundary term and the variation of the good boundary term are equal. That's what we will do tomorrow and on Thursday. We will look for a boundary term that is written properly, and it will not be equal to the one we start with because that's wrong. It doesn't transform correctly, but its variation will be the same. And we will correct the action accordingly. And the new action will be this boundary term plus the same thing, the gamma-gamma action. Instead of the wrong boundary term, we put the right one. Gamma mu lambda alpha, gamma lambda alpha. No, there's too many lambdas. Lambda nu alpha. Okay, so the variations of the two actions will be the same because of this identity. Nothing will change, but this one will be written in a proper way. Actually, Yes. And let me anticipate. We cannot anticipate how it will look like because it takes a little bit of work. So, no, that's not the new action. That's not the new action. The new action, sorry, because we want to be sure that the new action will contain only a Lagrangian of Q and Q dot. So what about this one? What about this thing? So let's just a moment. So what can we do here? Let's say the Hilbert action is equal to there are some constants here now that is maybe annoying. Okay, let's keep track of the constants as well. Anyway, minus 1 over k squared, or 2k squared, integral of on the boundary of w lambda sigma lambda plus s gamma gamma. So this is something we can cancel. And S gamma gamma is equal to SH plus 1 divided by 2 k squared partial m w lambda sigma lambda. So from the point of view of the variational principle, S gamma gamma is correct. From the point of view of diffeomorphisms, SH is correct. This is neither of the two. This is not correct. So what should we do? We should improve the action by means of the new boundary term, which has the same variation. Yes. But until I give you the final form of the boundary term, you cannot say that you are not convinced that it will give a decent Cauchy problem. So let me see if I can give it to you now, or we will have to wait, because it's a little bit involved. It requires a discussion and introduction of submanifolds, a little bit of differential geometry. Yes, and it will be okay, but it will not be visible now. So you have to wait till tomorrow or Thursday. That's it. And if you want, that is equal to S gamma gamma plus 1/2k squared times something that does not, that will have the same variation. That we have zero variation, the difference. Okay, so we need to talk about submanifolds now. Basically, we have to check that this boundary term, the new one, will not depend on delta q dot, the variation. Yeah, it will not, but we have to wait. So, submanifolds. We need to study submanifolds because the boundary is a submanifold. There is a little bit of work now. Let's say that M is a manifold of dimension 4. With metric G mu. And then we consider sigma to be a submanifold of dimension 3. And with a metric, the metric that will be induced by G mu nu. Let's see how it will be induced. Well, little by little, because this requires some introductory work. First, we show that there exists a unique normal vector to sigma. There exists a unique vector n normal orthogonal to sigma up to the normalization. What does it mean that it is orthogonal to sigma? That it is orthogonal to all vectors that are tangent to sigma in every point. So let us consider a basis V1, V2, V3 of vectors that are tangent to sigma in a point P. So, submanifold, sigma, vector, normal. This is obvious if you are in a Riemann context, but we are in a Lorentz context, so we will see that the vector n, the normal vector could square to 0, could be light-like, and space-like, could be null. Null means that it has a square equal to 0, but the conclusion is always true. There is always a unique vector n orthogonal to sigma up to the normalization. Let V0 denote a vector tangent to M in P. Let's say belonging to the tangent space to the tangent space TMP. Think with the tangent space to M in P. So since sigma is three-dimensional, its the tangent space in P is three-dimensional, and the tangent space P is also a point of M, and the tangent space of P to M in P will be four-dimensional, and therefore there will exist some V0, which is a vector belonging to this that is linearly independent of V1, V2, and V3. Of V1, V2, and V3. Then V0, V1, V2, V3 is a basis of the tangent space. Now I see that here I'm using a different notation. I don't remember which one I used, but here I see this notation. Let's use it. Is a basis of TPM. Okay, we cannot do much more today. So let's stop here.